Hello, welcome to another Game Dev Diary. So I made a big breakthrough in pathing recently, and I wanted to do a deep dive to explain the algorithm I'm using. Um, it may be that someone in the past has invented this or whatever and documented it. I couldn't find anything on it. So I just wanted to share what I've come up with. I also looked at Unity's nav mesh. But everything I found on it was how to set up nav mesh within Unity and not how it actually works. So I don't really know how it works or if it could be applied, or if that same kind of concept could be applied here, but I wasn't able to make any progress there. So first we got to go over a little bit of terminology. So doing a direct path check is where you take lots of tiny little steps between the start and the end point and then check every cell that it intersects with along the way to make sure each cell is pathable. So this is used in all the algorithms I'm going to show you today, and it's pretty expensive because you have to do a lot of tiny checks. It's not just one for each cell, because you can see some of these dots, there's several dots that intersect a particular cell. But for this direct path check to really be accurate, it'd have to be wider, because right now it's just a thin path forward. It'd need to be as wide as its character. To get around that, because it's already expensive, what I've done is made it so that there's bumpers on the character. So right now I have it set to just direct pathing. It's gonna, wherever you tell it to path, it's just gonna, even if it's through a wall, it's gonna try. So if we take that path, because of the bumpers, he kind of slides off the wall. And then if you give him a path that he can't follow, he'll slide a little bit, and then when he detects he's in a position where he'd just be thrashing back and forth, he cancels the path. So these bumpers are active in all the different pathing algorithms that we're about to look at. So I wanted to show you guys that first. So cell-based pathing, let's look at that first. So what this is doing is going cell by cell using the A-star algorithm to find a good path. And a real quick recap of A-star, because A-star is another thing that's used in all these algorithms. A-star examines nodes one at a time. It keeps an open list of nodes it's still investigating, and it keeps a closed list of nodes it's already accounted for. And the reason it's so effective is because it makes reasonable guesses about which nodes it should investigate next. So this educated guessing makes it so it doesn't really have to it doesn't have to turn over every rock before it finds the a good answer. That educated guessing that it does is called a heuristic, and the heuristic has two components. It has the distance back to the start, which is an exact measurement because it knows the path it has to take to get back to the start wherever it is in the algorithm, and then the distance to the target, which is an approximation because it doesn't know what other obstacles are going to be in the way getting to the target. So distance to start is exact, distance to target's an approximation. And if you're interested in confusing newbies when you're talking about this, you can call the distance to the start the G cost and the distance to target the H cost. I obviously don't like those names though. But so this is just basic cell-based A-star. And one of the problems with this is, well, let's just follow this path. The character kind of, especially when you're going diagonally, he kind of bounces back and forth. This is more notable noticeable if I turn off the pathing here. You see how he kind of bobs back and forth? I didn't like that very much. So something else we do here is path smoothing. So what this does is it tries to make shortcuts. It does these direct pathing checks after it has the cell-based path established. It does direct pathing checks to see which ones it can take out of the loop, and that is extremely expensive to do, but it produces a much more natural path. So follow that around, and you can see the character kind of bumps up against the wall. That's those bumpers I was talking about. Alright, so that's cell path smoothing. Let's see, so this is a pretty reasonable pathing algorithm at this point. I'm not really satisfied with it because it's really expensive, especially if you use the cell smoothing. So I want a game that's really heavy on simulations. I want agents that, you know, make up a simulated ecosystem, little simulated villages and stuff that are all operating when the character's nowhere nearby. So getting a really fast pathing algorithm is important, and also having really natural paths I think is important too. One option I considered was maybe having the agents use path smoothing when you're looking at them, but not use path smoothing when you're not looking at them. But then you get like a Heisenberg thing that, you know, where observing actually changes the outcome. So I'd really like to use path smoothing even when you're not looking at the agents. So I came up with something that actually achieves this, and I think is really cool. So if you've watched some of my older videos, you've seen this visualization before. This is pathing regions. They're part of each chunk's pathing metadata, and when you remove walls or put them back, all the metadata, including these regions, is rebuilt for each chunk. And a pathing region is defined, it's just a rectangular area where there's no pathing obstacles. So if both you and your target are in the same pathing region, you can just make a direct path to it without even doing a direct path check. You can just assume that you can move directly towards the target. So what I had before was I'd plan a path at the region level, and then I'd smooth it. And this would be faster because you're not having to, there's fewer nodes to check. You know, you're not having to check every little cell along the way. You do it at the region level first and then smooth it. So it just runs a lot faster that way. But the breakthrough I've made is to add another concept to this. So you see all these little white dots? Those are what I'm calling anchor points. And anchor points are little places in the chunk's pathing metadata that occur at all the convex corners along the the walls and such. And part of the metadata checks that they do is they figure out when they're formed. They figure out which other anchor points in the chunk they're connected to, and adjacent chunks as well, to handle transition from one chunk to another. So if I mouse over one of these, you can see this visualization shows which other anchor points it thinks it has a direct path to. And this is really useful, and that's a very expensive process, but it only happens when the chunk's metadata is being formed, and then it doesn't have to redo that every frame or anything. The only time it has to redo it is if a new block is added. So it's kind of doing all the hard work up front and then leveraging that information. So the theory is, and I don't know if this theory is right, but the theory is if I do an A-star path through these anchor points, that will give me the fewest possible nodes in the path, and it will also give me a path that does not need to be smoothed. So it's pretty much the best of all worlds. The problem is trying to create temporary anchor points that are not at convex corners, temporary anchor points that represent where the character is and the destination, and incorporating those temporary anchor points into the existing anchor point web. So that could be an extremely expensive process. So just if you were going to treat them like any other anchor point, you'd have to do a direct path check between like the character's position and every anchor point in this chunk and every anchor point in every adjacent chunk, which is just extraordinarily expensive, and that would kind of defeat the purpose. So the breakthrough I made was combining regions with anchor points. So each anchor point knows what region it's in, and each region knows what anchor points it contains. So when we try to plan a path, what we're going to do is connect the character, the temporary anchor point from the character, to all the anchor points on the region path that we make. So if I click right here, well, we still got it set to, alright, we're not going to use cell pathing anymore. Okay. So let's say we move here. Well, let's move here. That's a good example. So here, what we do first is we make a region path that'll go from this C13R3, 13R2 to 1829 and 18.3. Those are just the names of the regions. So it will plan a path, this region path, and then when it tries to connect to anchor points, you see it's not trying to connect to this guy up here. There's no connection to him because it only tries to connect to anchor points on that region path, which makes it so much faster. And then after it's connected both the character start point and the region and the target endpoint, then it does a star through that anchor point web, and the result is a really good path that's formed really quickly. So that's a lot to take in. That's a lot to take in, and I didn't have very good visuals. This is just like all my other videos, really poor, production quality. But the result is a really efficient path. So I'm gonna stop the character movement real quick so you can see what's going on. Now there's a shortcut it takes. First thing it tries to do is do a direct path to the endpoint, and if it does that, it doesn't try to connect to any other anchor points. But when it can't do a direct path, that's when it connects the start and the end to other anchor points in that region path. And the result is a really fast, really accurate path. So whenever you're doing anything with performance, you can't just go off, the silly harebrained theories that you come up with. Like, this should be faster in theory. You got to measure it. So that's something I've done here too. So here you have the cell path, the time it takes to do the cell path, and this is because I have path smoothing on, this is the smooth cell path. Now path smoothing doesn't apply to the region anchor path. So if you do a direct path, the region anchor thing's still a lot faster. If we have to go around an obstacle, that's where the cell path, where the region anchor path starts to look nicer performance-wise than the cell path. And if you do a really complicated path, you see that took 33 milliseconds, and this region anchor path took a fraction of a millisecond to plot. So that when you get lots of bends and turns in the path, that's where the region anchor path really starts to separate itself performance-wise from the smooth cell path. So that's an enormous, I'm not going to pull out a calculator, but it's over 33 times faster, obviously. So really awesome pathing. I've been focusing a lot on the foundation of this whole thing. Who knows what I'll work on next? I'm terrible at predicting what I'll be interested in working on next, but I'm really happy with how this pathing turned out. I might try to adapt it to be able to work better with larger characters, or I might just move on to something else and come back to the larger character thing later. But either way, I hope you are able to nerd out on this as much as I was. I hope you liked it. All right, thanks for watching.